So things are starting to get more interesting. I'm on number 29. A sample of size n equal 400 of bags of oranges showed an average weight of 24 ounces. Suppose those weights x had a normal distribution and that sigma was 1.5. Part A says, give a 95% confidence interval for the mean orange weight. So a 95% confidence interval, the formula for confidence interval again is x bar plus or minus z star sigma over root n, like that. That's if we know the standard deviation. If we don't, we're going to have to make a t interval, but so far we haven't had to do that. The z star value for 95% is 1.96, x bar is 24, sigma is 1.5, n is 400, yay. One way to do that confidence interval calculation is to compute the margin of error. So just look at 1.96 times 1.5 over square root of 400, and you get 0.147, and so that means the interval goes from 24 above that by 1 point, oh dear, I wonder which one of those is right. I have this thing where I transpose numbers. You might do it too. 1.96 times 1.5 divided by 400 to the 0.5. 1.47. So I guess this must be 1.47. Oh yeah, it is. Okay. So that's a good way to double check. It turns out I didn't plan it that way. 1.47 above 24. And a 1.47 below. So if I add 1.47 to this, I should get 24, which I do. So that's with sample size 400. It says, suppose we use a smaller sample size. Smaller sample sizes make wider intervals. You can think of that this way. If you collect less information, you're less sure about where the value is. So for the interval to have a good chance of containing the true value, it has to be wider. Or you can look down here. If you make this smaller, the margin of error gets bigger. Part C says if we want the margin of error to be at most 0.1 instead of the 0.147 that we got, in other words we have to increase the sample size to make that happen, and we also want a 99% confidence interval which would tend to be wider anyway, so it's going to accentuate the need for a larger sample size. What sample size is needed? The formula for sample size is z star sigma over the margin of error squared. Z star sigma over margin of error needed squared. I sure hope I got that without transposing numbers. I got 38.64 for the inside. We're going to square that. 1493.05, and then we always go up to the next larger number. Otherwise we don't quite get the margin of error we need. We get something just a tiny bit larger. So 1494 is the correct answer. Over here on 30, it says production of peanuts. Is it peanuts? Yeah, peanuts. It says it's 2,900 pounds per acre, and then lower on it says 3,000 pounds. I'm just going to take 3,000 pounds here as the production. So make a correction on your sheet. That 2,900 should be 3,000. So 3,000 is typical production, sigma is 578. A new plant food gives a sample mean of 3080. So that's slightly bigger than 3,000. That's pretty good news. We averaged over 60 plots. That's quite a few plots to think about, and we're going to test at the 0.05 level if the plant food changed the yield. So before we did it, we didn't know what was going to happen. Maybe it would go up, maybe it would go down. So we're doing this changing yield calculation. You would hope it goes up, but you're just testing to see if it changed it at all. So that means the null hypothesis is mu is 3,000. The alternative for changed is not equal to. If it said we wanted to check whether the new plant food increased production, then I'd be allowed to put mu greater than 3,000. It just says change. So you got to look for the key words in the statement when you're doing hypothesis testing, and what are they trying to find out? Was it an increase, a decrease, or just a change? Each of those has a different alternative that you have to put down. So we go ahead and compute z. The z I'm using is x bar this time. For the z for x bar looks like z is x bar minus mu over sigma over root n, like that. And so the x bar we got was 3080, the mu we're considering is 3,000, sigma is 578, the number of samples, the sample size was the 60 plots. So I did that, I get 1.11. Now, if you're used to computing z values, you know 1.11 is really not considered that unusual value. You have to get something closer to 2 before you start to see an issue that this z probably isn't something I would have seen in an experiment. So we're pretty sure we're not rejecting the null hypothesis, but let's keep going on. We go to table C. We find z star for a two-sided p-value of 0.05. We get 1.96. So basically you have to beat 1.96 in a two-sided test with alpha equal 0.05 to reject the null hypothesis. So we're not going to reject the null hypothesis, but let's just see. It says, what do you think the p-value really is? So I went down to the table, z star and two-sided p, and here's some z stars here. Here are the corresponding two-sided p-values. The 1.11 falls between 1.282 and 1.036. So as these z's get smaller, the p-values get bigger, and so the p-value you get is somewhere between 0.2 and 0.3. Upstairs though it says, okay, the p-value is between 0.3 and 0.2, so not less than 0.05, and so since it's not less than 0.05, so we fail to reject HO. So that says, in practical terms, there's no evidence of a change in yield because that tiny a change between 3000 and 3080 could easily happen just randomly. It kind of looks good that it happened, but it's the kind of thing you would see even if you didn't apply any changes to the situation. 3080 is something that could easily happen. So that's just life. You're left in limbo. Did the plant food do it, or was this just random variation? I can't tell. We often get numbers like this just randomly from plant yields with 60 plots if the mean was 3000. And so we see it, and it's pointing in the right direction as far as maybe increasing yield, except it could be just happen randomly. So the only way to tell if it's really doing any good is to keep repeating the experiment and see if we can get consistent results in that direction. This is just one observation. It's not good enough for us to claim there's been a change in yield based on the new plant food. So there we go. That's pretty close to the end of what we know how to do in the class, so that should make you feel good that we actually did something that you might be able to use. Confidence intervals and hypothesis testing kind of draw in on everything we've done in the class, and we're not done yet.